Okay, so let's get started. So several things. So first of all, about the lectures. This class will end this Thursday, so December 8th. That's our last lecture, and we are going to cover lecture 26. So the final exam will cover 20 to 26. So first of all, for the homework, homework 11 is due this Sunday. That's December 11th. So please try to finish that before Sunday so that I can upload the solution before that. And homework 12, we will not have time to do that. So what I did is that I uploaded a video on my YouTube channel. The name of the video is called Homework 12. Okay, so I went over all the details of this homework 12, all the problems of homework 12 in that video. You can check the video for the details. And the final exam will cover up to homework 12. And for the final exam, it will be the same as the midterms. So I will give you several days up to a certain deadline. You can find a 2 or 3 hour time slot to work on it and submit. And it will cover everything we learned after midterm 2. Yeah, and later on, I will upload the homework solutions for 10 and 12. For 11, I will try to upload it in the weekend, over the weekend. Okay. So are there any questions regarding this plan?
I did have one question about the final. So
Okay.
how long will we have the final? Over what period of time will we have to find those 3 hours to take it?
Yeah, so let me just quickly check the calendar. So it says now class ends on December 8th, and we should have you're right, final exam period, that's December 12th to 16th. So looking at the calendar, 12 to 16, that's next Monday to Friday. Okay, so it's basically next Monday to Friday. I think we can find a 3 days period of time. For example, now the homework 11 is due on Sunday. And so how about we do 14 to 16? Yeah, let's say 14 to 16, and the deadline will be Friday, 12 p.m., 12 a.m., let's say. Yeah, 3 day period from Wednesday to Friday, and then I will grade it over the weekend, and hopefully final grade will come out before 19th. Yeah, so I will upload these details. I will create a page, Canvas page later on with all these details. And if any of you have any conflicts with that period of time, but I don't think so, feel free to contact me. We can always make this flexible. Yeah, I think the final exam will include maybe 5 to 6 problems to solve. Okay, so if there's no other questions, we can continue the lectures. We are at lecture 24, still 2 lectures away. So last time we discussed all these 4 different types of conversions for sequence of random variables. This is the key technical tools that we are going to use to analyze the random process. We have the strongest convergence is almost sure convergence and mean square convergence. They imply the convergence in distribution, and which further implies convergence in, they imply convergence in probability, which further implies in distribution convergence. And the only way to verify this, the convergence behavior of a sequence of random variables, is to follow the definition. Strictly follow the definition. Now, we are going to talk about a sum of random variables. So basically, when we have in many cases, we consider a IID distributed sequence of random variables, especially in the case of random process, which we will talk about it in later in the lecture 25. We are curious about such a big random variable Sn, which is the accumulation of all the so usually this sequence of random variables or this random process occurs over time. So this K represents a time index, and this Sn is basically a random variable that accumulates this random process up to time n. So it is an accumulation effect. And we will see this kind of big random variables in many examples, especially in communication and signal processing. So let's consider this basic setup. So suppose we have a sequence of random variables xk, and they are IID. Okay, they are identically distributed, meaning that they follow the same distribution. They are independent. Okay, so this makes everything much easier. Now, suppose for every such random variable, we know the CDF function, we know the PDF function. They are the same for every xk because they are IID. And suppose we know the mean and variance for each of these random variables. Okay, so all these basic statistics are given. Now we can look at this accumulated random variable Sn. Since Sn is a summation of all these random variables xk, which is a linear function, right, of x1 to xn. So it's basically a linear function of multiple random variables, and we know, and we can calculate the mean and variance based on this function. So to calculate the mean, we can apply the linearity of expectation because this is a linear sum. So basically, it equals to, by linearity, it equals to sum of the mean of each xk. You can pull the mean inside this summation, and that will give us, so every xk has mean mu, so this will give us n times mu. So that is the mean of this accumulated random variable. It's basically n times the mean. Now, for the variance, we can also leverage the variance formula. We have variance of this sum of these random variables. Now, because xk's are independent, right? So the variance, okay, the most general variance formula would be, so the variance of this sum is the double sum of the covariance, right, between xi and xj. But now in this case, xi and xj are independent, right, for I not equal to j. So basically, if they are independent, the covariance is 0. So all is left is the sum over all the cases where I equals to j, right? So that gives us k equals to 1 over n, the covariance between xi and xi, which is the variance of these individual random variables. And we know the variance of each one is sigma squared, so this gives us n sigma squared. So basically, we have the mean and variance of this big random variable, Sn. So you can see that for this accumulated random variable, the mean scales with the number of random variables that involved in this accumulation. And also the variance also scales with linearly with this number of random variables n. So as we accumulate over time, the mean is increasing and also the variance is also increasing. And based on these statistics, we can prove the weak law of large numbers. This is a precise statement of the theorem, weak law of large numbers. Now, this theorem says that let's consider an IID sequence of random variables, right? Each has mean, mu, and variance sigma squared. So the setting is basically this one, it's the same setting. Okay. And then we have the following. If we consider this empirical mean, if you look at Sn divided by n, right? Sn is the accumulation, the sum of all the random variables up to n, and divided by n. So this is basically the empirical mean. If you write it out, it's 1 over n sum over k from 1 to n, xk. Okay, right. So basically, my pen is not working. Okay, I'm gonna refresh this page. So, okay, let me, oh no, okay, now it works. So Sn divided by n is the empirical mean. The empirical mean. And the empirical mean of this sequence of random variables, which is a random variable, right? Because this is a linear function, linear sum over all the previous random variables up to time n. So linear function of these random variables, which is again a big random variable. Now this random variable, you can call it, you can give it a name like a UN, right? Whatever notation you like, you can call this UN. This is a sequence of random variables, right? Because for every n, this sum will define such a random variable. So this is a sequence of random variables. And the weak law of large numbers says that such a sequence of random variable converges to the true mean of xk in probability. And this is a constant function, right? This mu is a constant, but we can still understand it as a random variable. So this random variable has no randomness. Okay? So this sequence of random variables converges to this constant random variable in probability. Okay? And this is the key. It converges in probability. Now, when you describe convergence of random variables, you have to specify among those 4 types of convergence, which we are talking about convergence in probability. So this empirical mean random variable converges to the true mean probability. which makes a lot of sense, right? Because the empirical mean is essentially an empirical estimate of the mean. And all these xk's, they have the same mean. So once you, as more and more experiments that you perform, this empirical mean is going to be more and more accurate. But accurate in what sense? Well, in the sense of this convergence in probability. Now, if we write out the definition of this convergence in probability following the previous lecture, right, this is basically what we are looking at. This is the convergence in probability. Meaning that if you pick any arbitrary small epsilon, and you look at the probability that this empirical mean deviates from the true mean bigger than epsilon, right? You look at the probability of this event for any arbitrary small epsilon, this will go to 0. This probability will go to 0 as you push n to the limit. So this is the precise statement of weak law of large numbers. Well, so when we talk about a law of large numbers, it's not just about empirical mean goes to the true mean. It's all about in what sense, in what type of convergence are we look does this empirical mean converge to the true mean? So here for the weak law, why do we call this weak law? Well, weak means that, as we mentioned before, convergence in probability is relatively weak. This one is in the middle. These two, convergence in probability and distribution, these two are relatively weak types of convergence. So this one is stronger than in distribution, but still weaker than almost sure and mean square. And that's why we call it weak law. And of course, next we will talk about strong law of large numbers. But let's look at how this is proved. How this is proved? Well, basically, we just need to prove. First of all, we calculate this probability, right? And then we push it to the limit, show that it converges to 0, following this definition. Okay. So we look at this probability first. The probability that this empirical mean deviates from the true mean bigger than epsilon. So what we are going to do is we're going to provide a upper estimate of this probability and show that this upper estimate goes to 0, right? Because this probability has to be non-negative. If the upper estimate goes to 0, so it will goes to 0 for sure. So this is the general strategy. But to provide an upper estimate, because we are looking at the probability of an event that described by an inequality, so this motivates us to think about all those concentration inequalities that we have introduced. So here we are going to utilize the Markov inequality. So what we do first is to, first of all, we write out the definition of Sn. So we have this sum, right? Sn divided by n is this empirical mean, minus mu constant. So we can combine this. Okay, so this is just plug in the definition of S. That does not change anything because here we have this is a positive number bigger than epsilon size to the power of 2. That does not change this inequality. Okay. So why do we want to raise it to the power of 2? Because next we are going to, it is easier for us to leverage the Markov inequality later. Right? Okay, we raise it to the power of 2. This is equality. Nothing has changed. Now, next step, we move this coefficient to the right-hand side, right? So because of the square, when we move it to the right-hand side, we have n square. Right? Well, n square, epsilon square, and then we get rid of this 1 over n on the left-hand side. Again, it's just a rearrangement of these coefficients. And then I'm gonna view this guy, this big square, as a non-negative random variable. Right? because it is a function of all these random variables, x1 to xn. So it is a random variable. And moreover, it is defined by a square. So it is non-negative. And so this is a non-negative random variable. And then we can apply the Markov inequality. Markov inequality says that for any non-negative random variable, x, we have this inequality, right? For any non-negative random variable with finite mean. Okay. So we view this as the non-negative random variable, and this as the A in this Markov inequality. And according to the Markov inequality, this probability is upper bounded by the expectation, the mean of this non-negative random variable, divided by n squared epsilon squared. And this is the interesting part. The mean of this non-negative random variable happens to be the variance of this random variable. Because if you write it out, it's the sum of k from 1 to n xk minus mu to the square. Okay, let me write it this way. So I remove this parenthesis. So this guy, sum of xk times minus n times mu. Right, because here it's the sum over this entire term within the parentheses. So if I expand it, I get n minus mu. So this random variable, this is a random variable, right? This is Sm basically. Sm minus its mean, because the mean is n times mu. We have derived that. A random variable subtract the mean, taking squared, and then takes the expectation outside. This is precisely the definition of Sn, of the variance of Sn. Precisely the definition of variance. We have derived that the variance is n times sigma squared. Okay. So the numerator is n times sigma squared. Denominator comes from here, it's n squared epsilon squared. And you can simplify, you get sigma squared divided by n times epsilon squared. And this goes to 0 because no matter what epsilon you fix, right, epsilon is bigger than 0, any arbitrary positive number, no matter what epsilon you fix, sigma squared is a constant, epsilon squared is a fixed number. So if you let n goes to infinity, this guy will go to infinity. So this proves that indeed this probability goes to 0, and we have the convergence improbability. And in particular, in the proof of this weak law of large number, we have a very coarse estimate of this probability. So this probability is roughly bounded by this term. Okay, you can use this to roughly estimate this probability. Now let's consider one application of this weak law of large number. This is an example. Let P be the unknown fraction of voters who support a particular candidate. And we want to estimate this P. Okay, we want to estimate this P. Now, the way we do this is very simple. We randomly interview N voters and report the fraction of these N voters who support the candidate. This is like an empirical estimate. You interview N people, see how many of them say yes, and that's empirical fraction is an empirical estimate of this P. But we want to understand the accuracy of this empirical estimation. Right? That's the challenging part. So we want to understand how many voters should we interview? How many voters should we interview so that the reported fraction, which is the empirical estimate, is within 1% of the underlying true parameter P, with a confidence level bigger than 95%. Okay. I know this sentence is very hard to understand, so let's read it again. So how many voters should we interview so that the empirical estimate, the reported fraction, right, this empirical estimate is within 1% of this true P, true parameter P, with probability at least 95. So with at least 95% of confidence, we can say that if we interview this many of voters, the empirical mean will be within 1% of the underlying true parameter. Because of the randomness, right? No matter how many voters you interview, this empirical mean can always have some probability to be very far from the underlying truth P. So that's why we add this confidence level. What we can say is that if you interview a sufficient number of voters, you are more confident to say this claim. And this is exactly an application of weak law of large numbers. Let's look at this example using the technical tools that we just introduced. So let xk denote the case voter's preference. And according to the first sentence, if you randomly pick a person, he or she will have a probability P to support this particular candidate, and 1 minus P to against this candidate. Now, this is a Bernoulli random variable. You random for each random person, the preference follows such a Bernoulli distribution. And of course, we have the mean. Bernoulli mean is P, and Bernoulli variance is P times 1 minus P. But we can calculate this. Now we interview N people. And the number of supporting voters among these N people is basically the sum of these Bernoulli random variables. Right? Because if the case person says supports this candidate, then we have 1, right? So sum of these Bernoulli random variables, this sum represents the total number of supporting voters within these N people. And apparently we know that because the sum of Bernoulli random variables, so Sn follows a binomial distribution. So we know the distribution of Sn, but we know that this binomial distribution is relatively complicated because it involves combinatorics. So so we want the reported fraction, okay, from out of these N interviews. So what is the reported fraction? Well, this is the total number of voters that you observed from these n people divided by n. So this would be the empirical fraction that you were going to report. Right? This is you interviewed n people, and Sn of them turns out to be the supporters. So this is empirical estimate. Sn divided by n, right? So what you want now, the last sentence, translating the last sentence to the probability language, we are looking at this probability. The entire. Okay, let's do this one by one. We want that. So we are looking at this event. The reported fraction is within 1% of P. This is your reported fraction. Within 1% of P, meaning that the difference between these two is within 1%. Right? This is the event. We want that so that this event, this entire event, happens with probability at least 95%. So the probability of this event happens with more than 95%. And then how many voters n should we interview so that this happens? So how many voters of n should we interview so that this guy empirical estimate is within 1% of the true mean, right? With confidence more than 95%. And in this case, it's easier to work on the complementary case due to the weak law of large numbers. So instead of considering this less than equal to, we are going to consider equivalent to the complementary case. The deviation bigger than or equal to 0.01. So if 95%, then the complementary event will be smaller than 5%, right? So these two are equivalent statement because they are complementary to each other. Okay, so this is basically what we want. We want this probability to be less than equal to 0.5%. And the right-hand side, the left-hand side is essentially the law of large number. If you look at the law of large number, right, the deviation between the empirical mean from the true mean is bigger than epsilon. In this case, epsilon is 0.01. So apply the bound that we derived in the law of large number. Apply this bound, this one. This bound says that this probability is upper bounded by this number. And this is a coarse estimate, but we can apply it here. So this probability upper bound is number. In this case, epsilon is 0.01. So you plug in epsilon equals to 0.01 here, you have 10 to the -4. Sigma square, in this case, sigma square is P times 1 minus P because it's Bernoulli. Each xk is Bernoulli. So it's P times 1 minus P in the numerator. So I guess here we implicitly assume the P is 50, for example, P is 50%. Then this will be 1/4. But you can always modify these parameters. And the rest of the step will be the same. Okay. Now this is what we get from the weak law of large numbers, but we want this one to be at most 5%, because this is what we want. We want this probability to be guaranteed to be less than 5%. Right. So a sufficient condition is to make sure this upper limit is smaller than 5%. So we set this upper limit smaller than 5%. We get the answer to be 50,000. Right. So you have to, based on this model, if the underlying model is a 50-50 model, is like a 50% folders will support it, and other 50% will against it, then you have to interview at least 50,000 people in order to have such a confidence. And this is a simple way to determine the number of voters we need to interview. And of course, this is a sufficient condition because we use the weak law of large numbers, and this could be a coarse estimate. Now, if we have a tighter estimate, then we may be able to reduce the number. And we will talk about this. We will revisit this example again later on. And the next thing is the strong law of large numbers. We have the weak version, we will have the strong version. The strong law of large numbers, the setup is exactly the same as the weak law. Right? We have a sequence of IID random variables, mean, mu, and variance sigma square. Right? So basically, under the same setting, we have two different claims. One is the weak law, one is the strong law. So this is because the proof of the strong law of large numbers is more challenging. So that we usually talk about these two different laws separately. Now, basically, it says that under the same condition, IID sequence with mean mu and variance sigma square, we can have a stronger convergence. We can actually show that the empirical mean converges both in the mean square sense and in the almost sure sense to the underlying true mean. So if you go back to this picture, right? Weak law of large numbers says the empirical mean converges to the true mean in probability. Strong law says that we can actually show convergence in almost surely and in the mean square sense. That's the strong law of large numbers. And these are the precise definition of these two convergence types. Now, the proof of the mean square convergence is simple because for the mean square convergence, we just need to show that this mean goes to 0. Now, if we look at this mean, this is the empirical mean subtract. This is the empirical estimate. Subtract the mean, taking square, and then take expectation. This is exactly the definition of variance. The definition of variance of this random variable. Right? Because the mean of this one is exactly mu. Right? Random variable subtract is mean, raise it to the power of 2, taking expectation. This is exactly the definition of variance. So this is essentially the variance of Sn divided by n, which is this empirical mean. And because they are independent, so we have the variance formula. First of all, the coefficient, we pull out the coefficient. Out of this variance, we have 1 over n squared. And then the variance of the sum of these independent random variables is the sum of the individual variance. So this is essentially sigma squared divided by m. Okay, so this mean is sigma squared divided by n, which goes to 0 as n goes to infinity. So we proved this mean square convergence. So this one is relatively easy to prove. And for the almost sure one is this, so I will not go over details of proof. If you're interested, you can follow this proof. But what I want to comment is that this is a short version of the proof, which is based on this additional assumption. Okay, the assumption is to require that the fourth moment of the random variables bounded. The reason is that with this assumption, the proof is shorter and simpler. It's kind of elementary. However, we can actually prove this statement without this assumption. But that proof is much more involved and more challenging. So it's not out of the scope of this course. So in the end, the statement of strong law of large numbers is very weak. The assumption is very weak. We don't need any requirement on the moment. But actual proof of this one is very complicated. But in the end, we can just apply this strong law of large numbers as long as we have a sequence of IID random variables with mean, mu, and sigma square. So we know it actually converges in the mean square sense and also in the almost sure sense. Okay. So this is a strong law of large numbers. We are so in both of the weak law and strong law of large numbers, we are basically looking at this random variable, right? This empirical mean, and we are trying to understand its convergence behavior to the true mean. So this is essentially the convergence of the sequence of random variables to another random variable. Now we can also talk about its CDF function, the distribution. Right. So we have this Sn, right? Sn is okay. So basically, up to this point, we have shown that, like, using the weak law and the strong law of large numbers, we have shown that this empirical mean, this random variable, converges to this constant random variable in some sense, right? In probability, almost surely, or in the mean square sense. Now, the next one we are going to introduce is the central limit theorem, which talks about the CDF function associated with this Sn. Right. And remember that Sn is a sum of x1 to xn. Now here we basically do a standard normalization. We look at this random variable yn, which is a normalized version of Sn, right? So Sn minus its mean divided by the standard deviation. Now, if Sn is that accumulated sum, well, each xk has mean mu and the variance sigma square, we have shown that the mean of Sn is n times mu. Right, so this is actually n times mu, and the variance is n times sigma square. So the square root of variance is sigma times square root of n. And following this standard normalization, we know that after normalization, this yn will become a zero mean and the unit variance random variable. And the variance is unit. Now, the central limit theorem talks about the convergence behavior of this random variable.
the normalized Sn. Okay, so let's look at the central limit theorem. Xk be IID sequence of random variables, well, each xk has mean, mu, variance, sigma square. It's basically the same setup. The conclusion is that this normalized Ym, this normalized Sn, Yn is a normalized Sn. Yn, this sequence of random variable converges to the standard normal random variable. It's a Gaussian zero mean unit variance Gaussian random variable. So this Yn sequence of random variable converges to this standard Gaussian in distribution. Now, which means that the CDF function associated with Yn converges to CDF function of the standard normal random variable, pointwise. For n in y, we have this convergence. So this is a definition of convergence in distribution. Meaning that if you look at, if you have a sequence of, if you have IID sequence with mean, mu, and sigma square, and you consider their cumulated sum. If you normalize this random variable, it always goes to Gaussian. So here, each xk can be arbitrary, right? Can be a Bernoulli random variable, can be an arbitrary random variable, as long as it has mean, mu, and variance sigma square. So their accumulation Sn will always have this Gaussian-like behavior. Right. So this is why we always say that in the limit, everything converges to Gaussian random variable. Everything becomes Gaussian because of the central limit theorem. And here I will not go over the proof, but I think the key question here is that why is this goes to Gaussian? Because if you look at the problem setup, there's nothing really related to Gaussian. Xk is IID. Well, everything could be IID, not necessarily Gaussian. And has finite mean and variance. Doesn't mean it's Gaussian, right? Xk can be Bernoulli or anything else. So, but it happens that in the end, this normalized Sn goes to Gaussian. So I think so that's why the proof is a little bit tricky. So we are basically showing that the proof logic is to show that the moment generating function associated with Ym converges to the moment generating function of the Gaussian. Because if we have this convergence, that means their CDF function has this convergence. And the moment generating function of Gaussian is an exponential function. And we can show that the moment generation function of Yn indeed goes to, in the limit, goes to an exponential function. So I will not go over the details here. But this central limit theorem is very useful because it says that if we look at this random variable, if n is very big, if you perform a lot of experiments, you have a lot of random variables to accumulate, and then this guy is very close to a Gaussian random variable. So we can approximate the probabilities of this random variable using the Gaussian CDF and PDF. For example, if we consider the previous Volter example, but this is exactly the same example that we were looking at. Now, previously we used weak law of large numbers. So here we can use this central limit theorem to get another estimate. right? In this case, every voter has probability P to support and 1 minus P to against the candidate. So we have the mean and the variance. This is basically a Bernoulli random variable, right? We have the mean and variance. Now we are looking at Sn, which is the accumulation, the total number of voters, total number of support voters out of n people. Now, following the previous discussion, in this problem, we want to look at this. We want to make sure this happens, right? The deviation of the empirical mean from the true mean bigger than 1%, right? The probability of this event happens less than 5%. And in the previous approach, we used the weak law of large numbers to get a rough estimate of this probability. But that estimate can be very, very coarse, very bad. So here we can use central limit theorem to get a much more accurate estimate. Now, according to the central limit theorem, Sn, if you go to this guy goes to standard normal random variable in distribution, right? And in this example, the mean of Sn is n times p. The variance of Sn is n times p times 1 minus p, right? So this is the normalized Sn, and we call it Yn. So following the central limit theorem, we can approximate this Yn using the standard Gaussian distribution. Okay. So we can just view this guy as a standard normal random variable. And then I do a transform because in this probability, I'm looking at Sn divided by n. So I need to somehow construct this empirical mean from this expression. So what I do is I multiply Yn by the new denominator. So we have this one, right? And then, so multiply the denominator to the right-hand side and plus n times p. So move this one to the right-hand side. And then divide everything by n. So on the left-hand side, we will have this empirical mean, and this is whatever we have on the right-hand side. So basically, this empirical mean equals to a linear function of Yn. Right? So something times Yn plus constant p. Because Yn is approximately a normal distribution, normal random variable. So this linear function, this random variable approximately follows this Gaussian distribution. Right? So this scaling only changes the variance, and this shifting only changes the mean. So basically, the empirical mean follows this Gaussian distribution. And we can use this one to approximate this probability. So here we are looking at empirical mean minus p. So basically this difference follows a zero mean Gaussian distribution with this variance. Okay, up to here, we know that we actually, so now we have an accurate approximation of the distribution of this random variable. So we are looking at this event, probability of this event. Now solving this inequality, this is absolute value bigger than 1%, meaning that either this one less than negative 1% or it's bigger than 1%. And these two, right, for each of them, we can approximate the probability for using the CDF function of this Gaussian random variable. And you can further do a normalization, right? So because this is not a standard Gaussian, so what you do is Sn, consider this random variable divided by the sigma, divided by the square root of this guy. So then you will have a standard Gaussian random variable. And then also these two numbers will also be divided by the standard deviation. So in the end, you can approximate these probabilities using the phi function, right, of a standard Gaussian random variable. Okay, this is our result. This is a very accurate numerical approximation of this one. Right. From the central limit theorem. It's different from the previous approach. Well, in the weak law of large numbers, that is a very coarse estimate. Here is a very accurate estimate. Okay. Now suppose P times 1 minus, suppose P is 1/2. So you get, so this product is 1/4. Okay. And you want this probability, you want this upper limit to be less than 5%, because this is what you want. You want this probability to be less than 5%. So here you simply set this estimate to be less than 5%. Now you look into the table of the phi function, you can figure out in integer n, so that this inequality is satisfied. Okay, so this is what you get. You need to approximately interview at least 9,600 voters, and this is much better than the previous estimate. As in the previous one, using the weak law of large numbers, we need to have 50,000 interviews. Here, following this approach, we just need to have less than 10,000. So 9,600 interviews, we can have 95% of confidence to say that the empirical mean is within 1% of the true mean. Yeah, so I think in the homework 12, you will see several problems where we need to use the central limit theorem. Okay, so so this is everything about sum of random variables, right? So here we basically when we accumulate this IID and random variables, they have a certain limiting behavior, basically described by the weak law of large numbers, strong law of large numbers, and the central limit theorem. The weak law and the strong law says that the empirical mean converges to the true mean in some sense, right? In probability, almost surely, and in the mean square sense. And the central limit theorem says that the such a normalized random variable Sn converges to the Gaussian distribution, Gaussian random variable in distribution. Okay. So all these are the limiting behaviors of this sum of random variables. And these technical tools are very important in order to understand the random process. Okay, so this is what we are going to talk about next. So a random process intuitively is very, very simple. It is basically a sequence of random variables. But here, in this process, we usually call the index of the sequence a time index. So this is a sequence of random variables happens over time. So we have xt, well, t is the time index. So at each time, we have a different random variable. So this will give us a sequence, essentially a sequence of random variables. Now, if t is discrete, of course, this is called discrete time random process. If t is continuous, we call it continuous time. And we have two different ways to understand this sequence of random variables. So basically, we have xt, where t is a time index, right? And the first way, because each xt is a random variable, so each xt maps omega to a real number as a random variable. So basically, if you fix a t, it is random variable, so it is function of omega. Right. This denotes the realization of the random variable xt under the associated with outcome omega. As omega belongs to the outcome space. So you have a sequence of random variables where each random variable is a function on omega, right? So basically you have two input arguments. One indexes the time, and one indexes the outcome that we're looking at. So there are two ways to look at this random variable. One is to fix omega, fix an outcome, and look at all the realizations of these random variables under this outcome. So we're looking at x, t, omega. We fix an omega, we look at all the realizations of these random variables in the random process. So you have x1 omega is the realization of your first random variable associated with this outcome omega. You have x2 omega, x3 omega, so at least goes on. So we call this a sample pass. So this is basically a sample pass of this sequence of this random process corresponding to omega. This basically the sequence of random variables. So this is basically the realizations of this sequence of random variables under omega. We call it a sample pass. So it's like a sample pass of realizations of this random process. So if you fix an outcome in the omega-1 in outcome space, and then all these random variables will have a specific realization over time. And you can draw this realization on a graph. So this is called a sample pass of this random process. This is like a realization of the random process. If you try a different omega, you get another sample pass. Right. So this is when you fix an omega, you look at the realizations of the random process. This is actually called a sample pass. Now the other way is fix t. Now when you fix t, you fix this t, basically you are looking at the random variable at time t. So this is xt, the random variable x time t. And if you go over all the omegas, basically you are looking at all the realizations of this random variable. Right? So this is a random variable. A random variable at time t. Okay. So essentially, we are still talking about a sequence of random variables. Right? But now this sequence is indexed by time. So there's nothing different. And because the random process is a sequence of random variables, so all the statistics of the random process can be described by the joint CDF function of all these random variables. Right? For example, if you look at the this set of random variables at different time steps, these are the random variables at different times in the particular random process. Now, in order to understand the behavior of this random process, we just need to understand the joint CDF function. Because if we know the joint CDF, we know everything about the relation among these random variables. So this is the most general information that we need to characterize the random process. Right? It's basically the joint CDF of all the random variables involved in the random process. But of course, this could be very, very complicated because usually in the random process, you have numerous random variables, and usually they are not independent. So in order to, so here we will not work on the joint CDF. Instead, we will work on some simple statistics. For example, we can define mean, correlation, and covariance of this random process, just following a very natural generalization of these statistics in the single random variable case. For example, all right, for this, I can look at the mean of xt, the mean of the random variable at time t, right? If you fix a time t, then this is a random variable. I can look at its mean, right? I can call this mu xt. So mu, the mean of the random process at time t is basically the mean of xt. It's a very, very natural definition. So basically, this mean is time varying. Depending on different t, we're looking at different random variables, and it will have a different mean. So this will give us a signal over time, the mean signal over time. So this is a mean of this random process. And we can also define this autocorrelation function. So autocorrelation describes the correlation between xs and xt, right? It's basically the correlation function between the random variable at time s and the random variable at another time t. Right? Because when we introduce the definition of correlation, right, for any arbitrary random variables, the correlation between x and y, right, is defined as expectation of x times y. Here is exactly the same thing, except that these two different random variables are coming from the same random process, but at different times. So we call one is XS, the other one is denoted by XT. This could be in general 2 different time steps. So we look at the correlation between these 2 random variables. And we denote it as Rx. So this describes the autocorrelation of this random process, capital X. And in particular, we are looking at the correlation between time S and time T. Right? These are the two parameters. So this is a notation. But essentially, the definition follows the standard definition of correlation. And autocovariance is the same thing. It's basically, we're looking at the covariance between XT and XS. This is exactly the definition of covariance between these 2 random variables. Right? It's XT minus its mean times XS minus the mean, and then taking expectation outside. So we call this the autocovariance functions. It's Cx, the autocovariance of this random process X, and we are particularly looking at 2 different times, S and T, right? And this is basically the covariance between these 2 random variables. And because this is the covariance, we know the covariance is related to the correlation in this way, right? If you expand this product, you will get a correlation term minus the product of the mean. But if you recall the covariance equals to the mean of the product. And this is the mean of the product minus the product of the mean. That's the covariance. So you can see all these basic statistics are defined exactly in the same way as those definitions of arbitrary random variables. Here, we're just talking about the different random variables inside a particular random process. And this is just a definition saying that if the random process has finite second moment, then we call it a second order random process. This is just a definition, finite second moment for all t. Because if this is satisfied, then all these statistics are well defined. Okay. For example, let's consider this example. Xt is a times bt times t squared, where a and b are independent Gaussian random variables. Okay. A and b are standard Gaussian. For example, x0 equals to a, which is a Gaussian. X1 equals to a plus b, sum of 2 independent Gaussians, right? X2, a plus 2b plus 4, right? So this is a linear function of these 2 Gaussian random variables. So xt is defined in this way. Find the second characterization of xt. Well, basically, you need to calculate all these statistics and just following the standard calculation. For example, the mu xt, which is the mean of this random process, right? Just follow the definition. It's the expectation of xt. But what is xt? Xt is a plus bt plus t squared. Well, a and b are zero mean Gaussians. By the linearity of expectation, you can, right? This is first mean is 0 because 0 mean. And this one is also 0 because it's a linear function times 0 mean Gaussian random variable. Right? It's also 0. The third one is a constant. So you get t squared. Right, the mean increases quadratically over time. And then the correlation, autocorrelation function, by definition, is the expectation of the product. The xt is this one, xs is this one. Right? You basically expand it. You have a lot of terms. Each term you evaluate the mean. For example, the first one, mean of a squared, but a is a standard Gaussian, right? So this is basically the second moment of this zero mean Gaussian, which is the variance. So it's 1. For this one, right, S is constant, so it's a mean of A times B. But A and B are independent Gaussians, so the mean of A and B equals to the product of the mean, which is 0. They are zero mean, right? So just work on these terms one by one. In the end, you get this one. So this is a function of T and S, only a function of T and S. And the autocovariance is the autocorrelation subtract the product of the mean, right? This is the autocorrelation. The mean is given by part A, so you can get this. So these two will cancel out. Okay, so it's nothing but just following the definition and do the standard calculations. And in fact, in this case, xt, if you look at xt, you fix a t. This is a linear function of linear sum of two Gaussian random variables, a plus bt plus t squared. So we know that linear sum gives us another Gaussian random variable. So with mean t squared, these two are both zero mean. So the only mean comes from here. Mean is t squared and the variance is 1 plus t squared. This is the 1 plus coefficient to the power of 2. By the property of variance. So basically, in this random process, the t's random variable follows such a Gaussian distribution. And moreover, we can look at these two arbitrary random variables at two different time steps, right? And they are defined in this way. And we can actually write these two equations in a linear algebra form, right? In a matrix product form. So we list these two as a vector. And this is given by such a linear equation on A and B. You can check by following the matrix vector multiplication rule, right? This set of equations can be written in this way. And the right-hand side is basically a matrix times A and B plus a vector. And we know that A and B are independent Gaussians, right? They're independent standard Gaussian random variables. So this A and B is like a standard two-dimensional Gaussian vector. So this vector xs and xt is a linear transformation of such a joint Gaussian random variable. It's Gaussian vector. And following the previous lectures where we talk about high-dimensional random vectors, you know, the linear transformation of Gaussians is also Gaussian. Right? So this random vector is joint Gaussian. And the mean is given by this. This is the offset. This is the mean part. Now the variance is given in this way. So basically, you need to evaluate all the variance, the covariance terms. Basically, if this is the equation, X equals to a matrix W times Y. Now this is Y, and this is U. And the covariance matrix of this random vector is given in this form. And in this case, covariance of Y, because A and B are IID Gaussian, so this is identity matrix. It's basically W times W transpose, and that gives this matrix. Okay. So if you pick any two random variables at two different times, they are joint Gaussian, following this definition. Okay. So I think I will stop here, and you can start to work on homework 11. And on Thursday, I think I will need more time to finish the last lecture. So I will be staying at home and record we will still meet over the Zoom, okay? But I probably will need more time to finish everything we have in lecture 26. Okay, so I will see you in the afternoon in office hour.